Throughout this video an image data structure has been used that allows flexibility while maintaining clarity. Image representation within a computer is best expressed as rectangular array. However, when dealing with more than one pixel data type across a set of algorithms, C data structure is the best solution for maintaining consistency throughout the algorithm ensemble. The data structure used here contains the rectangular size of the image, the type of data each pixel in the image represents and a pointer to the image data itself. The data pointer is a contiguous sequence of bytes whose type is described by the type variable. This animation shows simple C data structure and its relationship to an image. The following four types of image data pixels are used. Type 1 unsigned character. Type 2 integer. Type 4 float. Type 8 complex. Here type is typically represents the number of bytes used stored pixel in memory, 8 or 0 represents the number of bits in a single byte. The most popular pixel size is, of course, the unsigned character. Image transforms such as the Fourier and filters that operate in the spatial frequency domain use complex pixels. Other processes use float pixels. A complicity in programming arises in the accessing of the data using Cartesian coordinates. For example, 28 times 28 pixels of the input image, which is 784 pixels in total. Each one of these pixels represents a grayscale value, ranging from 0 to 1, here 0 is for black pixel and 1 for white pixels. Here, the rectangular image with rows equals 28 and columns equals 28, and if type 1, then it will require 784 bytes of storage be allocated for the data pointer. If it of type 4 float pixel then requires 4 bytes, that is, 4 times the previous amount will have to be allocated. However, access of the data by coordinate is tricky. We must convert from the Cartesian coordinate pair into a single dimension, so that we may index them in a linear data array. This data structure allows for easy representation of a large number of pixel data formats and conforms readily to the idea of memory as a contiguous sequence of bytes. One must also apply special data type modifiers when programming with MS-DOS systems. The far and huge keywords must precede large data space pointers. Proper use of these modifiers need to be properly handled. Consider this graphic representing an image, where each pixel is represented by a square and the total number of pixels is unspecified. The pixels have been lettered to facilitate the discussion. The first row of the image consists of the set of pixels, A, B, C, the second row is D, E, F, and the last row is G, H, I. We can easily generalize this to sets of columns as well. Using our image data structure and assuming pixels of type 1, the arrangement of data for this image in memory would be as follows, where each pixel requires 1 byte of storage. Data will point to a series of bytes that represent the pixel values in column row order. If type 2, and an integer in our machine requires 2 bytes of storage, often this is the size of an int, then the internal representation will look like this, so pixel A requires 2 bytes of storage, and so on. If the image is complex, type 8, and a float in the machine requires 4 bytes, the memory map will look like this. A complex image is a special case. Here, each data represents a real and imaginary component using a float data type. If the host computer requires 4 bytes to represent a float value, then each data in the data buffer will consist of 8 bytes, the first 4 bytes for the real part of the data, and the second 4 bytes for the imaginary part. Consider the small image to the left. We can visualize the pixels of this small 4x3 image, with pixel values A through L, in terms of their row-column coordinates. The programming description could be specified as the array, img. Pixel G would then be img of 1, 2. Alternatively, we can specify an image structure as described earlier, with a C statement struct image img. To access pixel G using our structure, we have to index into the data vector 1 row and 3 columns. The data in either case is stored as a sequence of bytes. The data pointer of the image structure will be initialized to point to the start of this sequence, as shown in the graphic to the right, after the space has been allocated. Using the structure format, the value of pixel G would be pointer to image data plus r times image.columns plus C, where r is the row number indexed from 0 and C is the column index. For this example, pointer to image data plus 1 times 4 plus 2 will yield the value G. There are other ways to formulate access schemes into linear arrays that have two-dimensional data mapped to them. Okay, let's conclude now. The most modern frameworks such as OpenCV uses the C structure IPL image, which uses 22 public attributes, including the 4 attributes that we defined here. Even more, the C++ version of same structure is defined as mat class, which uses more than 40 public member functions, 90 template member functions, with more than 64 data types, including the 4 data type that we defined here, along 8 primitive types, will facilitate better and faster access of pixel data from memory. Thanks for watching and your generous support, and I will see you next time.